Hey, hello guys, how are you? So I hope everyone is good. Can you just look at this small cute kitten? It's very cute, right? Okay. Oh, sorry for the inconvenience. Let's try to get into the video. And very much thank you for the big response for my simple regression. If you haven't watched it, just go and watch it. Watch that video before going through this video because like both of the videos are interlinked. So I highly recommend, and I'll also put that video in description. So coming to this video, without wasting any time, welcome to ML Made Easy. So in this video, I'm gonna talk about uh, first. Let's see what are the table of contents in this video. First things first, I'm gonna talk about what is overfitting. Overfitting, and secondly, what we're gonna learn about ridge regression. So I want to keep this video very short and sweet so that you guys do not distract and all those things. So first let's go into what is overfitting. So in the previous video I was talking about linear regression and machine learning, right? So what is machine learning? I'll just give a quick glance. So in machine learning, you'll give the input to the machine and it's like a kid, and you'll give the data and you'll show him, for instance, let's say the cats versus dogs. You'll give a sample amount of data in the sense like you'll give some sample images of cats and show it, this is cat, this is dog, and so on, so after a amount of time, you will be ready and you will be testing the kid, right? In the same sense, like you'll be testing the cat, testing the mission, sorry, like whether this is a cat or dog. So that's how the machine learning works. So for instance, let's say you have shown a kid just one image of the cat and memorize that this is a cat, and you straight go to the test that is this a cat or dog. So immediately the kid will confused and he will just remember the picture of the cat that you have shown. Until unless you show the same picture, he won't be able to identify it. So same thing happens with the machine learning as well. If the training data is very small, or else like another of the training data is very small, this thing happens. Or else the second situation is if the kid is too smart, in the sense like he goes very in depth of the futures. For instance, let's say he goes with the very in depth of these features of eyes and these ears and all, and he becomes so definite that only if these ears comes up with the images, he would be identifying whether it is a cat or dog. So those are the two cases. So one is like less training data, and the other one is like too much of complexity in the model. Will eventually lead to overfitting. This is called overfitting in the sense like uh, unable to give good results in the test data, or unable to give good results in the test exam, in the examination, you would say in the simple terms. So let's dive into overfitting, more into the overfitting. So I hope you guys have watched my previous video, linear regression. So here comes the regression part. So in linear regression, I'll give a quick glance. We'll be trying to fit a line for these data points, and by using cost function, by decreasing the cost function, we are trying to draw an uh, line basically, right? So that is called a best fit line. Will be, oh shit, sorry. So we'll be trying to draw a line which will have minimal error between these two oh, uh, training points. So what happens when you have less number of training data? For instance, let's say there are only 2 points in a data set. So what happens is the mission will eventually come to a point where it will fit a line through these 2 points. So something like this. So what happens then? So in the real world, you never have the whole data set. In the sense like if you search for cat and dog, you'll have billions of their images, right? Still you have the still you don't have the whole images of cats and dogs. Am I right? So that's how the data is. Like you'll never have the whole data. So you can't predict when is the next point coming in. Like the next point might be over here, or here, or here. So if your line is over there, like it's too much of error, right? So you need somewhere generalized, something like this, so that there would be minimal error. So we want a model which could generalize all the points, not only the training part. Something like just seeing how the tip of the ears are like, the tip of the cat ears are like this. So something like that, generalized line. We need something like that. So what you gonna do? So what uh so there are different ways to do this, but one of the most uh, used way is this ridge regression. It is also called as regularization of model. So let me talk more about it. So before that, let's go back to linear regression. What we do in linear regression, what we do, we have we'll try to fit a line which is theta naught plus theta 1 plus x. So we'll find the slope of this equation theta 1 using cost function every time you do the math, in the sense like you do the prediction, and find a minimal cost function which could satisfy our data set. So that's what we do, right? So what we're gonna do now is we'll add penalty to this. If the data is very small, we'll add a penalty, in the sense like I'll just show you in a minute. The penalty term would be lambda into summation of slope square. I'll explain you in a bit. So if there are only 2 points, so the error would be zero, right? In the sense like if the line goes through the points, the error won't be anything. Like it would be zero, in the sense like there will be like this point minus this point minus this point is, of course, it's a zero. So zero. So what you're gonna do is you're gonna add something to this error function uh, so that the error won't be zero. What you're gonna add is some positive value 0.5, something like that, so that the cost function increases. If the cost function increases, what you will modify the theta values so that it will be little bit of generalized. So our line, just a minute, guys. So instead of this, we'll be getting something like this. So theta is nothing but slope, right? Uh, this is slope, right? So the theta eventually here it is more plus slope square. What happens if the 0.5, for instance, let's say the slope value is 0.5. This slope value is 0.2 because like slope decreases when it becomes slant, right? It's normal thing. Uh, so what happens? Uh, the j theta values will be like this. Uh, this error and slope. Initially, the error might be 0. The slope would be 0.5 in this first case, in the sense like the error is 0 here. The error 0 and the slope would be 0.5. When coming to here, the error won't be 0 because like your model is bit generalized, right? Uh, just a minute, guys. Just assume these points are real world data. So to just give you a context, like why are we doing this? So Oh, our new best fit model would be like this. So the training error be this much. So the error might have increased in the sense like error might go to 0.1, but the slope decreases. So eventually the cost function value here it might be 0.5 whole square plus 0, but here it will be 0.1 plus 0.1 whole square. So the value might decrease. It might increase or it might decrease. So there will be a list of table, and between all those values, for instance, the value here is 0.25. Here the value is 0.1 plus 0.01, right? So the value might be, oh sorry, 0.2, right? So 0.04. So the value will be 0.14. So the value is 0.14 is very less in compared to 0.25. So of course our model will select this and will draw an best fit line as this. When now you have bit generalized, when the test data comes into picture, the error will be little bit of less when compared to this. So that's what you are trying to achieve in uh, ridge regression. So I have explained about slope, right? So I need to explain about this lambda. Lambda is like a hyperparameter where you see which one to give more preference. For instance, let's say you want to give more preference for the slope, for more preference for the slope instead of error, then you will give this multiply it in the sense like you will multiply more. You will give you will give more power to this slope in the sense like if the slope is very more when compared to error, so you will ask the model to decrease the slope. For instance, let's say the slope is 0.2. I'm sorry, the lambda value is 0.2. In the sense like you are giving more power. That is an hyperparameter in the model, which you can give as an input to the model. So that's about ridge regression. This is a normal, this term is normal linear regression plus this term will become the ridge regression. All you make the change is like in the terms of cost function, nothing else. Like still the model equation will be the same. All you are doing the change is in cost function. So now coming to multiple linear regression. So what now? So there are multiple thetas. So that's what we are there for. What we do is like you do the summation of the slopes, the summation of the square of the slopes, just like this theta 1 square plus theta square plus theta 3 squares. So uh, so it's basically the same thing, but instead of this only theta 1 square, just this one, uh, you will be adding all of these things squares. So we'll give you the final cost function that is called ridge regression. So because of this, you'll have more generalized model. So this is one of the way, and the other few common ways are increasing the training data set. Increasing the training data set also will give you more generalized model. And the other one would be the data augmentation. I mean like by doing some math in the data and creating more generalized data will also give you increase the number of points and the generalized form. So that's what about this video. I think you guys have learned about what is overfitting and what is ridge regression. And ridge regression is also called as uh, L2 L2 regression. I'll also talk about what is L1 regression. But for this video, I'm just sticking to ridge regression, which is L2. So I hope you guys liked it. Thank you.